coming to another one of our data science seminars hosted by the eScience Institute in partnership with the iSchool Data Lab and the CSE Interactive Data Lab. Before I go ahead and pass it over to Dave Beck with the eScience Institute, who will introduce our guest speaker, I just wanted to let you know that a welcome sheet, our sign-in sheet is being passed around. If you can please sign your name there. It's really helpful to see who's coming to these events, helpful for our metrics. And email is totally optional if you want to find out about other events like this. Fill in your email, otherwise feel free to leave that part blank. So thanks again for coming, and with that, I'll pass it over to Dave.
I just want to emphasize, she said metrics, and really what that means is our dollar arguments. So it's about money. Okay, so I'm very proud today to introduce Professor Shou-De Lin, who is a faculty member at CSIE, which is Computer Science and
Information Engineering.
At National Taiwan University. NTU is a Global Innovation Exchange, or GIX, partner. We're figuring out what that means.
Yeah.
At NTU, he leads the machine discovery and social network mining lab. He has degrees in, get this, electrical engineering, computational linguistics, and computer science. I feel like I left one out.
That's good.
From NTU, University of Michigan, and University of Southern California. He has received research awards from Google Research, Microsoft Research, and more Best Paper awards than I have time to talk about. And he was a visiting faculty fellow at Microsoft Research about 2 years ago. This I thought was really impressive, so I had to include it. His NTU team has won the data mining and knowledge discovery competition that the American Computing Machinery, ACM, holds 5 times. That's got to be a record. Yeah, right. Okay. All right, and with that,
thank you.
We'll let you get started.
Thank you, David, and thank you for having me here. So it's a great pleasure for me to come and consider it's summer. So I'm really impressed by this many audience, and I will do my best. I just learned that it's supposed to be a 45 minutes talk, and so try my best to be on time. So a short introduction of the lab I'm leading in NTU. It's called Machine Discovery and Social Network Mining. So we are doing a lot of things. Most of them are relevant to analyzing big data and using data to actually solve real-world practical challenges. And so let's move on to what I'm going to talk about today. So we all know like humans have intelligence, and right now we are trying to make machine as intelligent as human beings. And for human intelligence, we started from our kids is to memorizing things. Then later on, we start to learn things, and afterwards, probably after a couple of decades, people start to enter in their graduate school. They are trying to discover new stuffs in their study. Okay, so it seems like this is different level of intelligence and for human. And we want in our lab in NTU, we want to know like right now people already believe, at least probably most of us believe machine can learn to some extent. But we want to ask a further question: can machine be used to perform discovery, or even to assist human beings to perform discovery? So this is what my lab have been working on in the past decade. So we are trying to see if we can exploit the power of machine to perform or assist a human to perform discovery. And it's potentially high rewarding and also tolerates lower precision recall comparing to learning. But it's to some extent challenging because for discovery, we are not supposed to have a ground truth to learn from. Okay, so it's different from like a typical supervised learning. We have training data, which means we have XY pairs as examples to show the machine. But for discovery, we don't assume that exists. So that leads to a major challenge for this kind of research is to invest ways to discover things from unlabeled data. And you will see later on why. And so what I will introduce some of the past work in my lab in this direction. For example, one of the earlier work we were doing is to use machine to decipher ancient language. So it's an ancient Lin script. It's two-dimensional hierarchical and hierarchical language. And so we are trying to, for example, figure out the linear writing order for this kind of language. And we are trying to, so it seems like we were the first team in the world to really discover the one of the linear writing pattern in this kind of language. In one of the previous work, we were working on like AI as a classical poetry for Chinese classical poetry. So I suppose probably not everybody knows Chinese, but basically what we did is to use machines, try to learn from big data how do you write a Chinese classic poet. And if you understand Chinese, you will see those are the three poets written by our machine. And actually, we were selected from hundreds of them to get a three qualified one. So it's not really high precision, but it did produce some of the reasonable results. And some of you might have heard that Microsoft recently announced this Showice Poetry. So one of my students have been involved in this project. So this Showice Poetry takes a picture as input and generate a Chinese new poetry, and like this one. Okay, let me see if I get the pointer, or I can use this one. Right? Nope. Probably out of battery. Let's see. Let me see. Okay. Oh, good. Good. Thank you. Yeah. Okay. So this is considered as the input to the system, and it will generate some important text. For each text, it will generate a line of poet. And the amazing thing for Showice is like we actually submit those poets generated by the machine to a real a newspaper, and the edit anonymously. So the editor select it without knowing it's written by the machine. So in this sense, it already passed the Turing test in poets writing. So those are the poets that were selected by the editor from the newspaper. Okay. And so one of the recent work is to do Chinese lyrics rewriting. So it's like given an original lyrics, and we are trying to produce a rewritten version of it. And the goal is to, let me see, sorry. And we have several goals to satisfy for this kind of task. First, we want the rewritten lyrics to still fit the original tune. So you cannot create it freely, so it has to be performed using the same melody. So there's some constraint of it, and we want it we want to control the rhyme, and we want to control the emotion and preserve the semantics to some extent, and we also want the machine to demonstrate creativity. So this seems to be a very challenging set of goals to satisfy for the machine. And there are two plausible directions for solutions. Previously, people are mostly relies on the dual-based system, meaning that they can write a bunch of duals and to allow a machine to create things. And there are pros and cons for this. So for the pros, it's very easy to control things using the duals. For example, we can request the machine to produce lyrics with that rhymes, or control the emotion. We just make sure those terms occurs at some places. The problem for this kind of solution is it's not as creative as it can be. Okay, and right now in these days, people are more focusing on like a learning-based solution, which means we use probably deep neural network and generative models try to generate all kinds of interesting creative writings through it. But the big problem, big challenge for this kind of solution is it's really hard to control things. So it's really hard to teach the machine like it has to rhyme or it has to follow some sort of constraints. So we have actually we have a model that's emphasis on how can we to a certain extent maintain this creativity from deep neural network engine, but at the same time make sure those hard constraints are satisfied during the process of generation. Okay, so those are some of the sample results, and so if you understand Chinese, then you probably can see like it's to some extent like the length for each line is similar, and they can be segmented in a very similar way. So meaning they can be fit into the same melody or same tune easily, and so they might not like follow the same phony for rhyming, but they do rhyme. And we can also do like emotion transfer, and so the original, given the original lyrics, we can transfer to a happier one or to a more sad one. And so this is something we are focusing on in this task. We also work on a machine discovery for security. So homeland security is kind of an important area in these years. And so we are trying to, for example, identify suspicious individuals from a social network unsupervisedly. Or we are trying to perform the so-called side channel attack, attacking this card reader system using a data-based, data-driven solution. We are trying, one of the previous work published in KDD is trying to actually match users from different domains. Okay, so say you have a bunch of data, for example, from one electronic store like Amazon, and you have another bunch of data from Netflix, the other type of electronic store. And you know like people should probably to a certain extent have account for both sites, but those accounts might not be connected. They might not use the same ID or so on. So our goal is to actually find the identification across different domains and through a discovery procedure. Okay, so also two of the recent work, we are trying to think further. Okay, so previously those work are about discovery, and right now we are thinking whether discovery can actually help learning. Okay, so the goal is to improve the quality of a machine learning model through performing a discovery. So I will show you two examples. So one is what we call recommendation. So recommendation is one of the probably most popular application for machine learning, and normally this can be categorized or that can be described as a collaborative filtering process. So what do I mean by that? So we have a bunch of users and a bunch of items, and user did provide ratings for some of the items, but there are a lot of question marks, meaning those users have never been exposed by those items, so we want to predict the value for those question marks, then we can perform discovery. So this is what normally a collaborative filtering algorithm does. And people realize that, so if we somehow obtain the social information from users, then we can do a better recommendation job or a better job for collaborative filtering. So if we are told like these two guys are friends, so the underlying assumption is that those people who become friends, they might have similar tastes. And so those information can be exploited to build a better recommendation engine. Okay. But the problem is that sometimes the user social relationship might not be easy to be obtained. Okay, so our goal is that, so can we do recommendation assuming there is no social events or social information about those users, but we perform discovery on how they could be connected, and then we can perform a better recommendation. So the goal is to jointly solve two tasks. One is the discovery of friendship, the other is to perform recommendation. And our experiments show that if we do these two works jointly, it's possible we get a better result on the recommendation. Okay, so I won't go into the detail how it does, but we do have papers on that. And the second task is we want to do better on ranking and using the discovery of linked information. So I suppose people probably heard of PageRank. So PageRank is an unsupervised ranking algorithm. So given a big graph, it will provide the PageRank value for each individual node. It represents how important this is in this node is in this graph, and this can be performed unsupervisedly. So whichever graph you have, you could just throw it into a PageRank algorithm. It will produce the ranking for each individual node. And we did the experiment. We took a real data set from Facebook, and we performed this PageRank. And we found that during the experiment, we intentionally removed some of the links from the data. Okay, so we found that it's not very surprising. The more links we remove, meaning that we hide more data, the quality of the ranking goes down. Okay, so this actually motivates us, like, because a graph can never be complete. So for example, for the Facebook, there are some friends you do have in the real world. They don't have a Facebook account, or they forgot to connect you through the internet. So through the internet, we always get an incomplete graph, meaning that there are some things that are missing. And this experiment tells us missing link can hurt the performance of a ranking algorithm like PageRank. So our idea is to perform discovery on finding those missing links and do ranking jointly. So a naive way to do this is to do link discovery first. Then once you discover those links, you throw it to the PageRank algorithm. It will produce the ranking for the nodes. But that's probably is not the ideal solution, because these two stages, the second stage doesn't actually help you to do better in the first stage. So if you solve it as a joint task, meaning that this ranking part does help provide some of the information to boost quality of the discovery, and then the discovery also help you to do a better ranking. So this is a joint task we are trying to solve, and we show that with this approach, we can get better ranking results from incomplete data. Okay. So those are the introduction of some of previous work we were doing. And in today's, in the remaining of the lecture, I will focus on one of the previous work we have done in discover missing links in the social network, which is published in KDD. Okay, so the link discovery task has been a long-lasting challenge in data mining society. So the goal is to predict the existing, the missing links between, or missing connections between people in a social network or in a graph. And we are facing a discovery problem. What do I mean by that? So say if we are providing a graph with friendship graph, for example, and we can use those friendship graphs to train a model to predict who should be friends. Then this is a supervised task. So we are using existing data to train a model to predict the missing data. But the problem we are facing is a bit different. So it's we obtain this particular data from Foursquare. I'm not sure if people know this Foursquare website. So it's a website allows us to provide the comments for different, for example, restaurants, for different places, and they this also is a social network mechanism. People can connect to each other in this social network, and just like Facebook. And so, but one major difference between Foursquare and Facebook is that in Facebook, whenever you post a message, people will click this like, and you know who actually clicked that like. Okay, so you can check. But in Foursquare, for privacy reason or whatever reason, they didn't provide. So people can click this like button to your post, but you won't see who actually clicked the button. So in the network, in this Foursquare, you only see that this post is liked by how many people. Okay, for example, 40, 50, but you don't know exactly who clicked that like. So our goal is to figure out who actually clicked that like using the count information and other social information in the network. So we consider this as a discovery task instead of a learning task because we don't have supervised signal who actually click this post to train from. So if for some reason Foursquare provides us some sort of training data, if it tells us who actually click this like button, then we can use that to train the model, then it's not considered as a discovery problem. And but for us, we don't have that information, then we still want to investigate who were the persons who click those like buttons, and then this becomes a discovery problem we want to solve. And so this is the data we obtain. So we have like users, and users, they could be friends, and those information are provided, and the users can own some of the items. Those items are the posts they posted on the website. And those items can associate with some attributes, for example, the category, the length, the length of the post, so on and so forth. And they can belong to certain categories, like for example, this post could be relevant to sports, the other one could be politics. And so each category can associate with some sort of attribute as well. So this is the information we obtain. And one key information I forgot to mention is like for each post, there is associated with a count, meaning like how many people actually click like. For in this example, this post has been liked by 2%, and this R3 post is liked by nobody. And the problem we want to solve is that among those users, we have seen which one actually click, or which two actually click this like for this particular post. Okay, so going back to this problem, so we ask human how they could potentially solve the problem. So human actually come up with some good hypothesis or heuristic that might be useful. For example, they believe people might like their own items. So right now, we don't really show who actually click this like button, so why not click on your own post, right? In Facebook, probably we don't do that. But in Foursquare, I suppose it doesn't hurt. And other heuristics, such as people with more friends may have higher tendency to like items. People tend to like their social neighbors' items in similar extent. So meaning like if we are friends, and if you post multiple articles, I either click like to all of them, meaning like I'm probably very close with you, or I don't click like to all of them. For example, people tend to like items in the same category as their own items. So if you like posting relevant information about sports, World Cup, soccer, and you probably have higher tendency to click like on similar articles. So those are the hypotheses or heuristic like human might use to figure out who click the like button. Then we are trying to solve this using machine. So we actually face several challenges. The first challenge is how those knowledge or heuristic can be incorporated into our model to help us or help the machine to perform this kind of discovery. Okay, so our solution is to model them as a potential function between random variables in a graphical model. Okay, so I don't have time to go into the details, but the vector graph model is a popular graphical model. In this kind of model, every individual node is a random variable, and for random variable that are connected, meaning that they are correlated or not independent. And so this vector graph model have a lot of good properties we can learn from. We can adjust the parameters, try to optimize certain probability. And so it's basically a measurement likelihood mechanism that allows us to produce this kind of, try to optimize the observation. And so how can we exploit the vector graph model to solve this problem? So first, we want to define our search space. So right now we are solving this task is who actually like which article. Okay, so meaning that we have, like, for example, we have in this example we have 2 users and 3 items. So there are a total of 6 random variables we have to decide. So for each person we have to connect it, pair it with an item, and this random variable means how likely this person click the like for that particular item. So if it's close to 1, then we will guess this person did click the like for this item. And if it's close to 0, then it's not. Okay, so so mathematically, what we want to solve is we want to estimate the probability of these 6 random variables in this particular example. And so this becomes a node in a vector graph, and those random variables are the ones we are trying to estimate. And show you on the left-hand side, it's original data, so it's written as a social graph. On the right-hand side, it's the model. Okay, so in the model, each node is a random variable. In the data set, each node is an individual object. So how do we incorporate different kind of knowledge into this discovery system? I'll show you an example. So for example, we have a hypothesis. People with more friends tend to like items. So in this case, we have to know how many friends are there for each individual person. So for each random variable is associated with a user and an item. So we have an attribute space that tells the system how many friends belongs to this particular user. So we need this kind of random variable saying the number of friends of a user. Similarly, we can we can encode this kind of knowledge. People tend to like their own items. So to model this kind of heuristic, we need a binary random variable telling that whether this particular user owns this particular item. Okay, so for this random variable, there is a attribute associated with it telling that it's 1 or 0. 1 means this user owns this item, and 0 means upside. Okay, so there are a bunch of other kind of heuristics that we can all encode it as an attribute on the bottom layer of the model. Okay. So it eventually turns out like it looks like this. So those are random variables, and those are the attributes associated with each random variable. And so those are observed. So we already know, for example, how many friends are there for each individual person, or whether this person owns this item. Okay, so those are the first layer of modeling in our graph, vector graph. And we can also encode more complex heuristic. For example, we probably want to do this. People tend to like their own item in a similar extent. So meaning like if I produce multiple articles, either I will click like for all of them or not for all of them. So like they do similar action to their own item. So to model this kind of complex heuristics, we need something like this. So for example, this user owns both items, R1 and R2. And so this tells us U1, R1, we make a connection between U1, R1 and U1, R2. So U1, R1 capture whether this user click R1, and this U1, R2 capture models whether this user click R2, and they should be correlated. And so we make a connection here. So on the second layer, we actually make connection in between random variables in the graph. For example, people tend to like their friends' item in a similar extent. So in the example, for example, U1 and U2 are friends, and U2 have two articles written, R1 and R2. And this heuristic tells us U1 will either like both of them or not like both of them. So it means that U1 R1 and U1 R2 and U2 R2 should be connected, and so we make connection here. So similarly, we can design all kinds of heuristics, and we can put it as a connection between different random variables. Okay, so people tend to have similar tests as their friends. So this tells us if these two are friends, they probably should have similar tests to this particular item. So we need to make a connection between U1 R2 and U2 R2. So these two random variables should be correlated. And so this is what the particular heuristic tells us. So after collecting all those heuristics, we actually generate a huge graph on the second layer. So on the second layer, there are more complex connections between different random variables. Okay. So eventually we have So after we have built this kind of graph, the next question we want to learn is, in a vector graph, we have to learn those parameters. Just like every machine learning model, we need to learn the parameters for the models. And normally, if there are training examples, meaning if people tells us which person click which item, then we can use those training examples to learn the parameters. But right now, we don't have training examples. So we cannot directly learn those parameters. So what can we do? But don't forget, although we don't have the training example, we have the total counts for each individual post, and we want to use that to learn the parameters. Okay, so here we introduce the third layer. This layer actually captures the count information for items. So for each item, it's associated a number of counts, and we want to adjust or learn those parameters on the first layer and the second layer to make sure the count actually matches the observed information. So how do we do that? Here is an example I will show you. So using the previous example, we have only 6 random variables to decide their values, and they are this here. And in the very beginning, we just simply assign equal probability to the equal weight to those parameters. So each parameter should associate with a link or like a function to model the connection between random variables. So consider them as just a bunch of a huge set of parameters. Okay. So in the beginning, we probably assign equal probability, or we can also randomly assign probability to the parameters. And then given those parameters, we can generate, so you can inference the likelihood for each random variables. So for example, after the first pass, those are the probabilities of each of these 6 different random variables. And we have the count, right? So for example, this R1 is liked by 2 people. But in the first stage, we got 0.6 for U1. So U1 has 0.6 to click this like. And U2 have 0.1 chance to click this like. And those are the only 2 persons who have the chance to click this like. So 0.6 plus 0.1 is only 0.7, which is very far away from 2. Okay, so this tells us the current assignment of weight might not be that good. So we can adjust the weight in a gradient ascent manner to make sure in the next pass we want to adjust the weight so the probability of these two random variables goes up. Okay, so what we did is like we do gradient ascent or some sort of similar things, then we can improve or increase the probability here to be better match these two. Similarly, this R2 is liked by 0%. Nobody actually click like. But the current model tells us it's 0.9 for U2 and 0.5 for U1. It's apparently an overestimate of probability. So we want to adjust the weight to make sure that goes down in the second pass of training. And in the third example here, so this R3 is liked by one person, but the problem is the probability are equally distributed. So meaning that these two guys has each of them have 0.5 chance to click this like. This is not very useful because in the real world only one person click that link, click that button. So we want them to be separate enough so we can make a good decision who actually click the like. So we want to adjust our parameters so that they are not equal. Okay, so make sure one goes up and the other goes down. So this is how we learn those parameters. Okay, so we try to learn the parameters to make sure the count of the items actually matches the probability inferred from our model. Okay, so how we did that? We actually introduced a technology called ranked margin learning. So in this kind of learning schema, because every individual random variable can be inferred for a particular probability, and we already know how many people click like. So if we rank the probability from the highest to the lowest, ideally we want, for example, in this case, there are total count of C. So we want the top C, the candidates with the highest C, the top C probability has as high as possible, close to 1, and the remaining has probability close to 0. So in this case, we can separate the users into two groups. The first group contains C candidates. They are very likely to click this button, and the remaining consider as the majority of the users, they have very low probability to click this button. So the purpose of learning is to maximize the difference between the accumulated probability on the left-hand side before this C and minus the accumulated probability on the right-hand side. So we are designing and learning a gradient ascent type of algorithms try to optimize this probability. And that's through this mechanism we can learn those probability that can eventually generate a set of groups that's more likely to click this button. Okay, so that's how we solve this problem. Okay, and so the third challenge we are trying, people might ask is like, I described several heuristics. Okay, those are built by human knowledge, and they might not be correct. They might be wrong, right? So it's like, I believe people with more friends might click like more frequently, but it's just my belief. It could be wrong. Okay, so we want this mechanism allows the incorrect hypothesis. And fortunately, because we are trying to learn those weights, we don't constrain those weights to be positive, meaning that some of the heuristic, if I eventually generate negative weights, meaning they will have upside of effect on the discovery system. So this allows us to avoid the dangers of incorrect knowledge in the model. Okay, and so we did some of the experiments, and so we are using 4 different data sets, including the Foursquare. So we actually ask the company to provide us some of the ground truths, and we don't use that in the learning and in the discovery process, of course. We are using that only to evaluate the results. And for example, we are trying to rediscover this repost, response, and citation event in those social networks. For example, in Twitter, there are reposts. So what we did is we hide all the reposts from our training data. So we don't tell the system who actually repost which Twitter, and we are trying to see if our system can rediscover who actually click that retweet button. Okay, and so those are of similar flavor, and we are trying to use them as an experiment, and we compare with several unsupervised learning techniques. Most of them are trying to rank the importance of different links or different nodes and use those ranking as the heuristic to produce the results. And we are evaluating using the area under RC curve and NDCG. Those are popular evaluation metrics for this kind of task. And the results show that our model actually outperforms all the other unsupervised solutions, and it seems by a really large margin. So this tells us it seems this kind of solution might work for trying to exploit the counting information in the data to perform discovery of the like behavior. Okay, so here comes to the conclusion of the talk. So our SOP for machine discovery, although it's the details varies from task to task, but generally what we did is we want to model this problem more or less as an optimization task. And because there's no supervised training signal, so normally we have to design a surrogate objective to learn from. And for those surrogate objectives, we do have signal about how good they are, and so we want to make sure those surrogate objectives are as close to the true objective as possible. But normally searching in this space, meaning that you have to search not just given objective. You need to search also in the objective space. That means you need a really huge computation burden could be imposed on your discovery system. So we need to, normally for most of the tests, we need to consider about the efficiency and scalability of the solution. Okay, and also like I do believe right now it's a big data era. So data are coming all the time. So there's this V as a velocity, means data are coming all the time. And because of this future, most of the data are unlabeled. Okay, so they are coming so fast, people might not have time to label all of them. And so how to leverage this kind of unlabeled big data is one of the key research challenge in our society and also for my lab. And so we are trying very hard to think if we can have a good solutions on this part. But I believe it will be getting more and more attention and given more and more data coming. Okay, so I think probably I still have 15 minutes and for QA and all other comments. Thank you. Sure. Lady over there. Yeah. What is? Uh-huh. The poetry generation? Okay. Let me see. So the one with picture? Yeah. Oh, that's a very good question. So our goal is to only show the system. So we are investigating the second part. Sorry, the second part, which is learning-based system. So in learning-based system means that we only feed the machine the data, but not the rules or constraints. Okay, so ideally we want to just feed in the data a lot of lyrics, and it has to learn like where to write, it has to write, and where to segment this and something like that. So it's like we are not teaching it through a supervised way. We are only feeding the lyrics into the model, and the model have to learn itself. Sure. Yeah, so I believe you are mentioning Dr. Kevin Knight's team working on. Yeah, so because I'm aware of that because he was my advisor. So actually, what we did is like, my belief is like they work in a, probably they have this post-processing stage to do that. And right now we are looking at some sort of like end-to-end solution that allows the system, attention-based neural network system to learn that automatically. And it seems we have an early stage success right now, but as I described to some of the people this afternoon, we had trouble understanding why it actually discover at which space to write or at which part to segment the data. And that's really fascinating to me. We are still trying very hard to figure out why the machine can learn these kind of things without actually teaching them. And hopefully we'll get some results and very soon, and probably I can tell you more about it. Yeah, thank you. Over there.
So in the second part of your talk, looking at likes and so forth, can you apply that to identifying whether an outsider can say, hey, this is a biased review, as opposed to a review that I can rely on?
Okay, so yeah, so that's I think it's a popular topic. It's similar to like fake news analysis, right? So people are trying to see if this news is fake or not. And I thought about it, and I think at this stage, my answer would be no. I guess we are trying to discover things from data, and it's hard to tell like if this is trustable or not from data unless we have some sort of sign or some sort of information about to teach the machine which is trustable, which is not. And so I do see some of the works done by others, they tackle this kind of problem like biased review by outlier detection techniques. They are trying to find those outliers. For example, they give high rating to this movie, but the post, the written comments doesn't really look like very similar to the other posts they provide high ratings. So this falls into this category of outlier detection, and my gut feeling is like probably that's a better solution for this kind of problem. Yeah. Okay. Yeah.
I have a broader philosophical question about machine
Sure.
discovery.
Sure.
In your earlier slides, you mentioned that low precision is tolerable because
Yes.
the reward is high.
Mm-hmm.
But there are domains where, for example, if you want to discover a novel gene disease association,
Yes.
having a high false positive rate,
Mhm.
generating many possible candidate genes,
Mhm.
the cost of validating this is very high.
Mm-hmm.
And I was just wondering if
Yeah.
that low precision constraint relaxation
Yeah.
of constraint is essential to machine discovery as a field, or is there like work
Yeah.
that tries to optimize that as well?
Yeah, I think this is a very, very good question. So we actually have talked to a biologist about this, and my answer would be it depends on what alternative they have. So for example, if they have another way to generate thousands of hypotheses and the precision is similar to our system, then this system is useless. But for some of the collaborators we talk about, they really have no idea. So they really don't know like whether this could be a meaningful discovery. So the system will then be considered as a way for them to filter out irrelevant stuff. So considering that originally 1 million possibilities, then this system like probably reduce this 1 million to 1,000. Still, they need a lot of efforts to justify the finding, but it's probably still useful today. So it really depends on what kind of alternative they have right now for them to perform this kind of discovery. But this is a really good question. Please.
Yeah, so you talked a little bit about these essentially potential functions.
Mm-hmm.
I want to know how you mentioned maybe
Mm-hmm.
figuring out, so you make some assumptions about the potential functions, so
Mm-hmm.
whatever kind of correlations you think there are, or whatever
Mm-hmm.
hypotheses you have.
Mm-hmm.
How do you test those in a purely unsupervised environment?
Mm-hmm. You mean test those hypotheses? Or?
Yeah,
Uh-huh.
well, so
Yeah.
there's a slide, I think a little later than this,
Yeah.
that meant that where you said
Do you mean like how to evaluate the result?
so not necessarily evaluating them. Do you have, so these are heuristics that people come up with.
Yes.
And then you include these in your model
Mhm.
and do some optimization.
Yeah.
And I guess what I'm understanding, are you optimizing for what you have labeled data that you're using? Or?
We are optimizing the counting information. So that's the only, like, we call it surrogate. We don't have the label data who click this,
Right.
but we have this count. So we want to optimize this count. We want the probability to match that count. That's what we use.
Okay,
Yeah.
sorry, I missed
Yeah.
that. Okay, thank you.
Yeah.
Can I put you on the spot real
Sure.
quick? We had talked earlier briefly about the work that you have in your lab
Mhm.
on teaching machines ethics
Mhm.
and machine learning.
Sure. Mhm.
Can you give us like a 2-minute description?
Sure. Okay, so we actually published 2 papers in this year, one in AAA and the other one in AIRS on this. And so the first work is to how to teach machine the general, like how to embed a reinforcement learning agent like a universal ethic behavior. How do we train that? Can we train ethical reinforcement learning agent using the typical data we gather from the regular life instead of geared toward a specific ethical behavior? Like, so the idea is like there are so many like universal rule we want to follow that don't run through the red light and to help the elder people when they fall down, whatever. So there are a lot of that we don't want gather learning examples for each of them to train a model. And so the solution we published in AAA is like, how can we use the normal behavior data from normal people and use those to train a universal model to help the machine to learn ethics. That's the first work. And the second work is like we envision some circumstances that in the future when everybody has an agent, and for example, the auto-driving car, some agent could be more powerful than others. And so you spend more money to buy a more powerful car. And you probably don't, if you don't have that much money, you can still buy an auto-driving car, but it's less powerful. So one particular problem we will face is like the powerful one will take over all the resources, or most of the resources, and leave the poorer one starving. And so we want to prevent this kind of situation to happen. So in that work, we propose a very simple mechanism that we can adjust the reward function in the reinforcement learning agent. So the stronger one won't be that greedy to collect a lot of resources at very short time, and so that leaves some room for the weaker one to survive. And so that's the second work we were doing. Yeah. Thank you.
Any more questions for our speakers?
Okay, thank you. Yeah. I think I'm on time, right?
Yeah, perfect. Thank you.
Thank you.
I took a lot of notes.
Thank you.
I got a little bit of reading to do, I think.
Great. Yeah. So, should I just?
Yeah, I think I can take care of that. And then, let's see, off.
Yeah, hopefully.